Welcome to the deep dive. Today we are diving deep into the world of time series analysis. This is really the fundamental engine driving pretty much every prediction you rely on.
Yeah, absolutely. Whether it's figuring out next year's budget or forecasting inflation or even just how many delivery trucks you'll need next week.
Exactly. It sits right at that busy intersection of, well, maths, statistics, and data science.
It really is the art, or maybe the science, of turning history into prophecy. And our listeners shared a really comprehensive stack of sources on this.
Yeah, they really cover the whole process, don't they? From just defining the basic ingredients of time all the way to these cutting-edge deep learning models.
They do. So our goal here, I think, is clear.
Right. We want to pull out the essential concepts you, the listener, need to understand how we actually transform that stream of historical data into a hopefully reliable future forecast.
And skip the overwhelm, focus on the framework.
Yeah, exactly. So let's start right at the beginning. What is a time series, fundamentally?
Well, conceptually, it's beautifully simple. It's just a sequence of observations, right? Where the measurements are taken in temporal order. Time is the independent variable.
And that order matters. That's
Yeah.
the key difference from standard stat.
That order is everything.
Yeah.
Yeah. In standard statistics, data points are often treated as independent. But here, the order creates dependencies. What happened yesterday strongly influences what happens today, usually.
Okay. Let's unpack this then. When we look at any time series visually, that squiggly line showing sales or temperature or whatever, there seem to be four key pillars.
That's right. These characterize the data. They're like the building blocks we need to identify before we can even think about modeling.
So what are they?
Okay, think of these as the fundamental vocabulary of time. First up, you have the level.
The level.
Yeah, it's the baseline average value of the series, kind of the anchor point. If you flattened everything out, that's your level.
Got it. So like if we wiped out all the peaks and valleys, that stable line would be the level.
Precisely. Okay, next is the trend.
Trend? That seems intuitive.
It is. It's the predictable, consistent upward or downward movement over a long period. Are your sales fundamentally growing decade over decade or shrinking?
Yeah.
That's the trend.
Right. Then we hit the component that, well, really matters for retail and lots of businesses. Seasonality.
Ah, yes. Seasonality. This
Yeah.
is the fixed repeating pattern. It could be weekly. Maybe sales always spike on Friday.
Or annually?
Or annually, exactly. Like the predictable dip in travel bookings every January. Our sources had a great example. Hypermarket sales forecasting.
Oh, yeah.
Those sales depend critically on the calendar week of Christmas. It happens every year, same time, fixed interval.
Okay, that makes the distinction for the fourth component, the cycle, much clearer then, because if seasonality is fixed, the cycle must be unfixed.
Correct. Cycles are also repeating patterns up and down, but they're usually longer term, and crucially, their duration is not tied to a fixed calendar interval like a week or a year.
So more like broader economic shifts.
Often tied to major macroeconomic factors, yeah. The business cycle, maybe recessions. They might last 5 years, maybe 10 years, but they aren't guaranteed to peak on December 25th.
Right. So if we connect this to the real world, understanding these four components is how huge operations think major U.S. retailers or big European airports forecasting flight arrivals manage their resources.
Exactly. They have to differentiate between, say, an annual summer travel rush, which is seasonality, and a multi-year economic boom driving overall growth, which is the cycle.
Makes sense. And you mentioned sources pointing out that this all follows standard data science methodology.
Yeah, absolutely. Before any fancy math starts, data scientists usually follow an established process, often CRISP-BM.
And the tools are typically Python libraries, pandas, Sklearn.
Those are very common, yes. Or statistical environments like R, or even visual tools like Orange. But whatever the tool, the very first step is always diagnosis.
Which brings us neatly to seeing and cleaning the data. Gotta look before you leap, right?
Exactly. You have to look at it before you can fix it. The simple run plot, just a standard line chart over time, that's the default view. But visualization is just the start.
It kicks off ADA, exploratory data analysis.
Right. And EDA is essential because you're trying to deduce the appropriate model from the data's characteristics. You don't just impose a model blindly.
Okay. And for just looking at one series like temperature over time univariate analysis, the sources highlighted something called the four-plot.
Ah, the four-plot. Yes, it's a really crucial diagnostic tool. Think of it like a quick, comprehensive checkup for your time series.
A checkup, what does it check for? What's it designed to tell us?
Well, it bundles four plots together. The run sequence plot itself, a lag plot, a histogram, and a normal probability plot.
Okay.
Analyzing these together helps answer two fundamental questions. First, is the data behaving randomly? Is it following a standard probability distribution, like the normal distribution?
And the second question,
Perhaps even more critical, are the underlying conditions that generated this data constant over time? Or is something changing?
that's a huge pre-check. Because data rarely arrives perfectly clean, right? So cleaning is mandatory.
Oh, absolutely. Mandatory.
What are the non-negotiable cleaning steps specifically for time series?
Okay, well, missing values are super common. We handle those through imputation.
Imputation, like filling in the gaps.
Yeah, replacing the gap, often using the mean or median maybe of the surrounding observed values, just trying to make a reasonable guess.
Makes sense.
Yeah.
What else? Outliers, those sudden spikes.
Definitely outlier cleaning.
Yeah.
But you don't just delete points arbitrarily. An outlier is typically defined as a point that falls outside a statistically calculated confidence interval
Based on what?
based on a provisional predictive model. So you sort of have to build a basic expectation first.
Just to find the truly unexpected points. Wow.
Exactly. We also sometimes use rule-based cleaning. This is actually one of the oldest techniques borrowed from databases. It's about checking data against integrity constraints, rules that must be true.
Like making sure a count of items is never negative.
Perfect example. And finally, scaling. Normalization or standardization. This is vital if you plan to use any model that's sensitive to the scale of the input numbers.
Like neural networks.
Neural networks are a prime example, yeah. They can get thrown off by wildly different ranges of the input data.
Okay, this is where, for me, it gets really interesting. Once the data is prepped, we formally break it down, decomposition.
Yes. The goal here is to mathematically isolate those components we talked about earlier. The trend, the seasonality, and whatever's left over the residual or error.
And how we do that depends on how those components interact, right?
Entirely. The choice of mathematical model here is dictated by whether the magnitude of, say, the seasonality changes as the overall level or trend changes.
Okay, give us that crucial distinction again. Additive versus multiplicative.
Right. We use the additive model when the seasonality's magnitude stays roughly the same, regardless of the trend. So if your average sales are 100 or they grow to 1,000, your Christmas boost is still, let's say, an extra 50 units.
So it's just added on top.
Exactly. The formula is simple. YET equals trend plus seasonality plus residual. A simple sum.
And the multiplicative model, when does that apply?
That's when the seasonal variation increases proportionally with the overall trend. If your baseline sales double, your holiday peak should also roughly double.
Okay, so it's a percentage thing?
Essentially, yeah. That model uses multiplication. YET equals trend times seasonality times residual. Most growing businesses probably need a multiplicative approach.
Our sources mention some powerful modern decomposition tools here, like STL.
Yes, STL, that's seasonal and trend decomposition using LOESS. It's clever. It iteratively refines the trend and seasonality estimates, sort of cleaning them up in passes.
And of course, Profit, developed by Meta, right? Known for its handling of seasonality.
Profit is very popular, especially for business forecasting. It has strong, specialized decomposition features built right in, particularly good with holidays and multiple seasonal patterns.
But wait, before we jump into these complex methods, you mentioned something critical earlier, the baseline.
Absolutely essential. Before you run any complex model, you must establish a baseline. If your fancy model can't beat the simplest possible prediction, well...
Why bother?
Right.
And that simplest prediction is the naive forecast.
That's the one,
Yeah.
the fundamental benchmark.
How naive are we talking?
Well, naive 1 is literally my forecast for tomorrow is just the value I observed today. That's it.
Okay, that is naive.
Naive 2 might be slightly more sophisticated, the
That's-
average of the last two values. But the point is, if your multi-million-dollar forecasting system only performs marginally better than naive 1.
You have a serious justification problem and cost problem.
Exactly. So assuming our model does beat the baseline, we need to know by how much. We need metrics to score success.
Right. How do we measure how good the forecast is compared to the actual outcome?
The two heavyweights you see most often in industry are RMSE, root mean squared error.
Used by Walmart, the sources said.
Widely used, yeah, like in Walmart sales forecasting. It's popular because it penalizes larger errors more severely, which often makes sense. A big miss is usually worse than a small one.
Okay. And then there are the percentage-based errors, MAP and WMAP. Why the what's the weighted part for?
Good question. MAPE, the mean absolute percentage error, gives you the average error relative to the magnitude of the actual value. It tells you the error as a percentage.
Which seems useful.
It is, but WMAP, weighted AP, is often far more insightful for business decisions. The weighting allows you to prioritize certain observations. I
Meaning?
mean, you can assign a higher penalty if your forecast misses during a critical period like Black Friday sales compared to a random Tuesday in March.
Okay. So you're essentially saying it's much worse to be wrong here. That connects the abstract math directly to business risk.
Precisely. You're betting your resources based on that forecast being right when it matters most.
I also noticed one specific metric mentioned for comparing sequences that might be a bit out of sync. Dynamic time warping, DTW. What's that about?
Ah, DTW is fascinating stuff. Imagine you have two recordings of someone saying the same word, but one person says it slightly faster or slower.
Okay.
Standard metrics, comparing point by point, would say they're very different because the timing doesn't align perfectly. DTW finds the optimal warped path to match the sequences, stretching or compressing time locally.
So it can see the similarity underneath the timing difference.
Exactly. It lets you compare shapes even if they're slightly out of phase. Very useful for things like comparing motion patterns or speech signals.
Okay, great. Now we move to the final stage, the modeling techniques themselves. We're covering a spectrum here, from simple smoothing all the way to deep neural nets. Let's start with exponential smoothing, ETS. How does that work?
Right, ETS models are based on a simple, intuitive idea. Recent observations are more relevant than older ones, so they assign exponentially decreasing weights to older data points.
Makes sense. History matters, but recent history matters more.
Precisely. The complexity scales with the components you need to model. The simplest form, simple exponential smoothing, SES, is only useful if your data has no trend and no seasonality. It's basically a weighted moving average where weights decay exponentially.
Pretty limited then.
Very limited, yes. If you have all three components we discussed, level, trend, and seasonality, then you jump to the full Holt-Winters seasonal model.
That's the ETS workhorse.
Oh, that's the one. Holt-Winters manages level, trend, and seasonality simultaneously. It uses three smoothing factors, usually called alpha, beta, and gamma, to control how much weight is given to recent observations for each component.
And the appeal is?
It's relatively fast, it's highly interpretable, you can see how it's making the prediction, and honestly, it's often incredibly effective for many real-world series.
Okay, if ETS, especially Holt-Winters, is simple, fast, interpretable, and effective, why do we need the next step up, the statistical powerhouse? ARIMA models.
Ah, good question. Because ETS, while great, makes fairly strong assumptions about the structure of the data. ARIMA models are designed to handle more complex autocorrelation structures, how a value relates to its own past values. But they come with a crucial requirement.
Which is?
The time series needs to be stationary.
Okay, let's nail down stationarity. We touched on it with the foreplot. Why does it matter so much for ARIMA?
A stationary series is one whose basic statistical properties like the mean and the variance remain constant over time. If a series isn't stationary, maybe because it has a clear upward trend.
Its mean is changing.
Exactly.
Sure.
Trying to model and forecast a non-stationary series directly with ARIMA is like trying to predict where a car will be in 5 minutes while it's accelerating, using only its current position. The underlying process is changing.
So ARIMA needs stability. How does it achieve that if the original data isn't stationary?
Through differencing. That's the IA. In ARIMA, it stands for integrated. You take the difference between consecutive observations, maybe once, maybe twice. This often removes the trend and seasonality, making the remaining data stationary.
Wait, if the model removes the trend by differencing, aren't we losing that information? That sounds counterintuitive.
It does sound like it, but you're not losing it, you're isolating it. By differencing, you stabilize the series so you can model the remaining, hopefully stationary noise or fluctuations predictably.
Okay.
Once you have a forecast for that differenced stationary series, you integrate it back, essentially reversing the differencing process to get the final forecast on the original scale, including the trend.
Ah, that makes perfect sense now. Okay, so the famous PDQ parameters in ARIMA stand for. P is the autoregressive part, using past values. D is the degree of differencing needed for stationarity. And Q is the moving average part, using past forecast errors.
You got it. And if you have seasonality, which standard ARIMA can't handle directly, you move to its extension, SARIMA.
Seasonal ARIMA.
Right. It adds another set of parameters, PDQ, plus the seasonal period M, like 12 for monthly data, to handle the seasonal patterns. Our sources do note, though, that figuring out the right PDQ and PDQ values can be, well, quite complex. It often involves looking at autocorrelation plots and can be pretty resource intensive.
Right, not always straightforward. And that complexity, I guess, drives the move toward more automated or specialized tools for certain problems, like for financial data with changing volatility.
Exactly. When the volatility itself changes over time, calm periods followed by wild swings, which is called heteroscedasticity standard models, struggle. That's where you need something like the GRCH model.
GRCH focuses specifically on modeling that changing variance.
Precisely. It models and predicts the variance, which is crucial in risk management and finance.
And for systems where the key drivers aren't directly observable, the sources mention state space models, SSM.
Yeah, state space models are a very powerful framework. The core idea is that the system we care about evolves based on an unobserved or hidden state.
We only see noisy measurements of it.
Exactly. We never see the true underlying state, just imperfect reflections of it. Think about tracking a missile. You don't see its exact trajectory, just radar pings.
So how do you estimate that hidden state?
And the mathematical engine for doing that, recursively updating our estimate of the hidden state with every new measurement, is the Kalman filter. It's fundamental to modern tracking, navigation, control systems, even areas of economics.
Wow, okay, so that covers a lot of the statistical ground. Moving towards more modern machine learning approaches. We mentioned profit again. Its strengths are.
Profit is really designed for business forecasting challenges. It's flexible, handles missing data and outliers pretty robustly, and models seasonality using Fourier terms, which makes it great for complex patterns like weekly and yearly seasonality plus irregular holidays. It's often easier to use for practitioners than, say, SARIMA.
Gotcha. But the final frontier, it seems, is deep learning.
For really complex sequences, especially with long-range dependencies, yes.
Yeah.
We move into the realm of recurrent neural networks, RNNs.
But standard RNNs had issues?
They did. They struggled with learning dependencies over long time lags due to problems like vanishing or exploding gradients. The breakthrough came with LSTM's long short-term memory networks.
LSTMs. They solved that gradient problem.
Largely, yes. They have internal memory cells and gates that allow them to selectively remember or forget information over long periods, making them highly suitable for sequence data, like text, or indeed time series stretching over hundreds or thousands of steps.
And even LSTMs aren't the absolute latest thing anymore.
Technology moves fast. The current excitement, largely driven by natural language processing, is around transformer networks.
Transformers, they use something called the attention mechanism.
Exactly. Instead of processing the sequence step by step like an RNN or LSTM, the attention mechanism allows the transformer to weigh the importance of all historical data points simultaneously when making a prediction for the next step.
So we can instantly look back and pick out the most relevant past moments, no matter how far back.
That's the core idea, yes. And they're proving very effective, now being applied successfully to time series forecasting problems too.
Wow. Okay. We've really gone from those 4 basic components level, trend, seasonality, cycle, all the way to transformers using attention. That's quite the journey.
It really is the full spectrum. We've covered the diagnostic necessity of tools like the 4-plot, that critical distinction between additive and multiplicative decomposition, and the whole modeling landscape. You now hopefully understand why you might choose a fast, simple Holt-Winters model, why stationarity is such a big deal for ARIMA, and when you might need the power and complexity of a Kalman filter or an LSTM.
Yeah, you, the listener, should now have a solid framework to assess the trade-offs cost, interpretability, complexity, accuracy for pretty much any time series model that gets put in front of you.
Which, interestingly, brings us right back to where we started almost.
Yeah.
Remember that fundamental benchmark.
The naive forecast. Forecast tomorrow is just what happened today.
Right, the absolute easiest model to implement. Zero computational cost, practically.
So we'll leave you with this final, maybe provocative thought. When we look at the immense complexity, the data requirements, the computing power needed for LSTMs, transformers, Kalman filters, how much of our actual decision-making improvement really comes down to just finding that small, incremental, but meaningful percentage gain over the absolute simplest prediction we could possibly have made?
Something to think about next time you see a complex forecast.
Yeah.
How much better is it really than just assuming tomorrow will be like today?